Okay, we're dealing with 6-1 polynomial functions, as you can see. This is on page 300 in your textbook. And really, I want you to turn over with me to the second page, and we'll take a look at this definition that they have here for a polynomial function. Kind of looks ugly. There are several pieces to it. You can notice, and this is the hard part for a lot of you, is to notice that the n's are going down. So the exponents n minus 1, n minus 2, which they don't show here, is going down until you finally get to x to the first, and then x to the 0, which is 1, and that's why you don't see it. So decreasing order of exponents, this is called standard form. And that is decreasing order of exponents. You'll notice that here's an example of one that's in your textbook. They have nice colors, but I'm going with the au naturel, black and white. The first coefficient is called the leading coefficient. This is called the cubic term because it's got a third degree polynomial. This is your quadratic term, which they don't list. I think it's in a different color. That's why it didn't show up. The quadratic term, the linear term, and the constant term. Okay, now the whole thing's called a polynomial. But the degree of the polynomial is right there. They talk about that. There's the degree of each term. Each term has a degree, but then there's the degree of the polynomial. The reason they call this standard form is because it has descending order of degrees. So you start with the highest exponent, count your way down. That's called standard form. The degree of the polynomial is the largest degree. The largest degree, as you can see right there in your textbook. Now they have this cool little chart. See if I can back up here a little bit. Hopefully it'll stay for me. They have this cool little chart that you should be looking at in your textbook, page 301, since you all have your books at home with you. We can classify these by their degree, which is this cool part of the table over here. The terms that we use for degree are constant, linear, quadratic, cubic, quartic, quintic. Those are the terms that represent the exponents. And you could see those right here, exponents. And they represent the highest degree. And then we can also classify them not only by degree, but also by the number of terms. So for instance, something that has one term is called a monomial. Something that has two terms is a binomial. Something that has three terms is trinomial. We run out of cool terms, so when we get to 4 terms or beyond, we say polynomial of 4 terms, polynomial of 7 terms, polynomial of 12 terms. I know that's not really eventful, but that's the way it goes. Now, in example 1 here it says, write each polynomial in standard form. There's no simplifying that I can do here. These are as simple as they are going to get. So it's not about doing any kind of math. It's about rearranging them so that they are in decreasing order of exponents. Now when you go to example B over here, you can see that you've got some like terms that have not been added together. Those things need to be combined. So we need to start out with the highest exponent, 3x, or highest degreed exponent, 3x to the third. Then we go to our next one, x plus x squared. And then lastly, we combine the linear terms together to get the last term. There's no constant term in this. I should say the constant term is 0. That's the best way to describe it. But that's getting them in standard form. Now, what are these things? This one back here. This is a quartic binomial. So there's a classification for the degree, and there's a classification for the number of terms. This one over here, cubic trinomial. It's got a third degree, and it also has 3 terms. You can practice some of these at the bottom, combining them, putting them in the right order, and then classifying them by degree and exponent. And really, quite honestly, that takes care of section 6.1. There's not a whole lot of things that I want you to learn there in terms of new material. I do want to direct your attention to page 306 on something called end behavior. These polynomials, when you graph them, can come in one of four basic shapes. Now, obviously there are lots of different ones, and they have lots of different things that can happen, but we're going to talk about four different basic shapes. End behavior is describing what's going on both ends, far to the left and far to the right on the graph. So in this case, in this polynomial right here, the left side is up and the right side is up. So when I ask for the end behavior, you're going to draw what looks like a set of parentheses with two arrows, both indicating that it's up and up. These are always on the up and up. The next type is both pointing down. As you can see, the polynomial both have end behaviors far left and far right that are going to go down, 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 down. This one, down on the left, up on the right. And this is the exact opposite. Up on the left, down on the right. And so what we're going to try to do is we're going to try to look at an equation and be able to tell what the end behavior is. Well, what I really need to know something about the, I should say, the end behavior is described best by looking at the leading term. The leading term is going to have a leading coefficient. And it's going to have a degree. The first thing I want to do is look at the lead coefficient. If it is positive, then the right end behavior is up. If it is negative, then the right end behavior is down. So that's the first thing I look at. Secondly, the degree. If it is an odd degree, then the left end behavior is opposite of the right end behavior. If it is even, then it's the same as the right. So now we can take a look. If we use those rules, we can take a look at these examples. For instance, 1x to the fourth. So that's got a positive 1, right? I'll write that a little bit bigger here. 1x to the fourth. That means that the right end behavior is up. Because it is an even polynomial, the degree, that means the left end behavior will be the same as the right. When I look at this one, it's got a negative 1, right? Negative x squared. That means the right end behavior is down. And because it's an even degree, the left is the same. Here I've got a lead term of x cubed. The right end behavior is up. The odd degree tells me that the left is opposite of the right. That's how we get the down on the left, up on the right scenario. Negative 0.3x to the third. Down on the right because I've got a negative leading coefficient. Odd degree means I've got an opposite on the left side. So that's how we can look at those equations and tell basic information about end behavior. Now, this information about end behavior tells me nothing about what's going on here in the middle. That is all determined by other things, but not the end behavior. So when you are describing end behavior, you're going to have to look at the leading coefficient and determine whether that 4 means up or down for the right. The odd degree, what does that mean for the left end behavior? So a few practice problems down here at the bottom of the page, but we'll go through a few in class together. But you'll also be able to do some of those on your own. 6-2 is about polynomials and linear factors. So we're going to see how these things go together. Polynomials can be written in standard form, but they can also be written in what's called factored form. So, for instance, it says write the expression x plus 1, x plus 2, x plus 3, all those factors being multiplied together, as a polynomial in standard form. Well, what does that mean? That means we're going to do a lot of foiling. Now, my suggestion on that, or how I would handle that situation, x plus 1, x plus 2, x plus 3. You know me, I'm going to box it. I know. You're going to foil it, some of you. Some of you like the box, some of you hate the box. Use it or don't use it. Whichever works for you. I'm just matching up. So I actually multiplied these two together right now, and I'm going to get x squared plus 5x plus 6. And now I'm going to multiply by x plus 1. What do you think I'm going to do? Yes, another box. And I got x cubed, and I got 5x squared, and I got 6x, and I got 1x squared, and a 5x, and a 6. Now I can add my like terms, giving me x cubed plus 6x squared, right, because those are like terms, plus 11x, because those are like terms, plus 6. That's the factored form. That is the standard form from the factored form. And they kind of show you something similar in example 1, but that's how I would do it. I would use boxes. I would not use, as they have kind of described, a few different techniques. You can use FOIL if you want. Same idea, just organized differently. Doesn't bother me if you do that. Okay, now you need to take something like this. This is going the opposite direction, right? 2x to the third plus 10x squared plus 12x in factored form. As you can see from what they did, the very first thing that I continually tell you to do is factor out the GCF. In this case, it's 2x. When you are factoring out, really all you're doing is dividing. So you're going through each one of these and you're dividing them by 2x. And that's where you end up getting your x squared and your 5x and your 6. Don't forget, your 2x has to be on the outside. And then you can continue to factor it, looking for two things that multiply together to give me 6, that add together to give me positive 5. And of course, those are going to be 3 and 2. But you can't forget, you've got your 3 factors. 2x, x plus 2, x plus 3. And that is your factored form right there. We're going to skip example 3 because it involves using the graphing calculator, and we're not using that right now. Something else you need to know. These are called relative minimums and relative maximums. You can tell that on this particular polynomial, it never stops going up and up and up and up and up, higher and higher and higher and higher and higher. Well, so there's never going to be a place where it actually stops going higher. There's also likewise never going to be a place where it stops going lower. These would be called absolute maximums or absolute minimums. But you can tell that there is a place inside this graph where if you just looked at a small snapshot of the graph, there is a low point. Or a snapshot here, there is a high point if you just look at that portion of the graph. Those are called relative maximums or relative minimums. Now, I am not going to ask you what are the relative maximums and what are the relative minimums. I don't think that's a fair question at your stage of the game of algebra to ask you that question. But I will ask you between what two consecutive zeros. Now, what's a zero? Fancy term for an x-intercept. between what two consecutive zeros will we have a relative max? Now we have three different zeros here. Our three different zeros are, it looks like negative 10, 0, and positive 15. Now, I've got to pick out consecutive ones. So I'm either going to pick these two right here, negative 10 and 0, or 0 and 15. But I'm not going to pick negative 10 and 15 because those aren't consecutive. So I look at the graph. If I'm looking for a relative max, it looks like it's between 0 and 10. So I'm going to say between 0 and 15. One way to write that notation would be like this, using brackets to indicate, you know what, I'm not even going to worry about that. Let's just say 0 and 15. When you write your answer down on your test or quiz, you're going to write 0 and 15. Now, as far as the next example is concerned, example 4, you're going to be finding zeros of a polynomial function. Find the zeros, then graph it. So there's two parts to this. Finding the zeros, well, that's easy. That means that the y value is 0. Well, that can only happen if either x minus 2 or x plus 1 or x plus 3, one of those has to be a 0. So set them equal to 0 and solve them, and you come up with 2, negative 1, negative 3. Remember that zeros of a function, that's a fancy term for x-intercepts. So you're going to come to your graph and plot your points. 2, negative 1, negative 3. You should also note that we can find the end behavior. Now I'll show you a fancy, easy way to find the end behavior. Take the firsts and multiply them together, all the firsts. The leading term from this is 1x cubed. 1x cubed, which has a positive 1. So that means my right end behavior is up. It has an odd degree, so that means my left end behavior is opposite. And so what I do after I find my end behavior is I come to my graph and I attach the end behavior. Now look where I'm attaching it to. I'm attaching it to the outermost zeros. I've plotted my zeros and I'm attaching it to the outermost ones. Now, here's the tricky part, or the not so tricky part. If we were to actually use a graphing calculator or plot out a bunch of points, we could find these relative minimums and maximums. But I don't really care what they are for Algebra 2 kids. So I'm going to ask that you draw a picture that goes something like this. It comes up and then it comes back down. Now you'll notice that my graph didn't exactly match their graph. Don't get hung up on that. Don't worry about that. What if I drew this one and I came up like this? No big deal. Remember, I'm asking you to sketch the graph, not draw a perfect graph. The important parts are, did I find the zeros? Check. Got them all. Did I plot them on the graph? Yes. Did I find my leading term and my end behavior and attach that in the correct way to the graph, the outermost zeros? What happens in between should be just going down below, coming up, coming down. But don't get hung up on how high or how low those things go. The factor theorem is simply something that expresses the idea that it says the expression x minus a is a linear factor of a polynomial if and only if the value a is a 0. Well, that makes sense. X minus 2 is a factor, factor, if and only if x equals 2 is a 0. Okay, an x-intercept. So those two things go together. We just kind of really talked about that several times here already. Trying to do notes upside down, huh? In example 5, it says write a polynomial function from its zeros. So they give me 3 different zeros. And as you can tell, they give me x They give me -2, 3, and 3. So, -2 gives me a factor of x plus 2, and 3 gives me a factor of x minus 3, and I got another one of those x minus 3's. What do you think I'm going to do? Yes, I'm going to FOIL or box it. The only way I'm going to get down to this thing down here at the end is to use foiling, or in my case, the box, which I will forego for right now, and if you need to ask me about that in class. Now, this last particular example illustrates something. When you have two zeros and they are identical, this is called multiplicity. In other words, the zero is used multiple times, so they call it a multiple zero. We can identify the multiplicity of a number. So in other words, on that last example, we could talk about zeros and their multiplicities. We had two different zeros on this last example. We had -2 and 3. Multiplicities refers to the number of times the factor was used. Looks like -2 or x plus 2 was used once, but x minus 3 was used twice. Those are the multiplicities. Ironically speaking, do you see that these two things, 1 plus 2, add up to 3? What is the degree of this polynomial? Oh, look, it's a third degree polynomial. So get that into your head. The multiplicities have to add up to the degree. Now, there are a couple stipulations on that, but by and large, the multiplicities will add up to the degree of the polynomial. We'll find out more information about that later. Okay, find any multiple zeros of that and state the multiplicity. Well, let's see here. Do some factoring. Factor out the GCF. Oh, look, it's x squared. When you factor out x squared, you're left with x squared plus 6x plus 8. Then you can break it apart into those two things. Well, neither one of these is being used more than once. These are both used exactly one time, so they have multiplicity 1. Here is your multiplicity 2. Now, what number would cause x squared to become 0? Yes, the answer is only 0. So in other words, it shows right here, x minus 0, x minus 0. Now, nobody's going to write x minus 0, x minus 0. I mean, you get laughed at parties when you write x minus 0. People are just going to write x. So x minus 0 times x minus 0 is a different way of writing x squared. So I know it's kind of seems weird here, but the number 0 is a 0. It says the number 0, and not only is it a 0, but it's a multiple 0, meaning it's been used more than once. This term meaning the x-intercept, so maybe we should interchange that. 0 is an x-intercept for this graph. In here you can see that -1 is being used twice. This one you'd have to do a little bit of factoring to see if you have any values which have a larger multiplicity than 1.